When the most powerful artificial intelligence available was asked to analyze what Google had just built, the answer that came back made the people reading it go quiet. Not because it was wrong, because it might have been exactly right. And if it was right, then the implications of what Google quietly announced in December 2024 extend so far beyond the boundaries of computing, so far beyond the boundaries of technology, that the word breakthrough does not begin to cover what actually happened. Because what Google built is not a faster computer. And what Google built is something that operates in a category of reality that our best classical machines cannot even approach. And when an AI system sophisticated enough to reason about the deepest questions in physics was asked to explain what that means, the explanation it produced left experts staring at conclusions that none of them were entirely prepared to sit with. The chip is called Willow. It is small enough to hold in the palm of your hand, built around 105 superconducting qubits cooled to temperatures colder than the vacuum of outer space, operated by a team at Google's quantum AI laboratory that has been working toward this specific moment for over a decade. And when Google announced its performance results in December 2024, the number that stopped the global technology and science community in its tracks was this one. Willow performed a computation in under 5 minutes that would take one of today's fastest supercomputers 10 septillion years to complete. 10 septillion years. Written out, that number looks like this, 10 followed by 24 zeros. The current age of the universe is approximately 13.8 billion years, a number so large it already strains human intuition. 10 septillion years is not just larger than the age of the universe, it is larger than the age of the universe by a factor so enormous that comparing them is almost meaningless. The fastest classical supercomputer humanity has ever built, given a head start at the moment the universe was born and running continuously without interruption until now, would not have made a measurable dent in the computation that Willow completed in the time it takes to brew a pot of coffee. The announcement wowed even Tesla and SpaceX CEO Elon Musk, whose own AI company xAI had just launched Grok 3, one of the most powerful AI reasoning systems ever built. And it was in the intersection of these two developments, the most powerful quantum chip ever demonstrated and the most powerful AI reasoning systems ever deployed, that the conversation producing the most unsettling conclusions began. Because when Grok 3 and systems like it were directed at the question of what the Willow results actually mean, what they imply about the nature of computation, about the nature of reality, and about the timeline of what comes next, the answers produced were not the measured, cautious, hedge-everything responses of a system trying to avoid controversy. They were the logical conclusions of a reasoning engine following the evidence where it leads without the institutional self-interest that makes human experts pull their punches. To understand why those conclusions land the way they do, you have to first understand the technical problem that Google's Willow chip solved, because it was a problem so fundamental that it had blocked practical quantum computing for nearly 30 years, and the solution turned out to be stranger than anyone expected. The central challenge of quantum computing has always been what physicists call decoherence. Qubits, the quantum equivalents of the classical bits that power every conventional computer, are extraordinarily fragile. They exist in a state called superposition, which allows them to represent not just 0 or 1, but both simultaneously. And it is this property that gives quantum computers their extraordinary power. But maintaining superposition requires isolating qubits from any interaction with the outside environment, because the slightest disturbance, a stray photon, a vibration, a tiny fluctuation in temperature, collapses the superposition and introduces errors. Controlling and reading qubits without causing errors has been the central engineering challenge of the field, because in previous systems, adding more qubits to increase power also increased error rates, meaning that the systems became less reliable as they became more powerful. This is the problem that Willow solved, and the solution is what makes the experts who understand it most deeply go quiet with something that is not quite comfort. Willow demonstrated that it could reduce errors exponentially as it scales up, a major breakthrough in quantum error correction that the field had been seeking for decades. In previous quantum systems, more qubits meant more noise, more errors, more computational chaos that degraded the output. Willow inverted this relationship entirely. The more qubits Willow employs, the fewer errors occur. The system becomes more stable as it becomes more powerful. This is not an incremental improvement on a known technique. It is a qualitative phase transition in what quantum computing is capable of, and it removes the single most significant barrier that had been standing between experimental quantum demonstrations and practically useful quantum machines. Google researchers described it as the first ever algorithm to achieve verifiable quantum advantage on hardware, surpassing even the fastest classical supercomputers, and demonstrating for the first time in history that a quantum computer can successfully run a verifiable algorithm that has no classical equivalent. When AI reasoning systems were asked to analyze what Willow's error correction breakthrough implies about the trajectory of the technology, The response pointed immediately to the exponential curve that makes this field so difficult for human intuitions to track correctly. The history of classical computing was shaped by Moore's law, the observation that the number of transistors on a chip doubled approximately every 2 years for decades, producing the extraordinary computational capability that powers the modern world. Quantum computing's scaling dynamic is fundamentally different, and in the most important respects, it is more extreme. Each additional qubit in a quantum system does not add computational power linearly. It multiplies it. A system with 210 qubits is not twice as powerful as one with 105. The relationship between qubit count and computational capability is exponential in a way that classical transistor counts are not, which means that the gap between what Willow can do and what its successors will be able to do is not the gap between this year's smartphone and last year's. It is the gap between a pocket calculator and the fastest supercomputer on Earth. And it will be crossed not over decades, but potentially over years. Google's most recent algorithmic work, published in Nature in April 2026, demonstrated the first verifiable quantum advantage running a real computational task, simulating the structure of organic molecules at a precision level that classical computers cannot match. The analogy Google's researchers used is worth sitting with. They compared it to the difference between sonar that tells you there is something at the bottom of the ocean and the ability to not just locate a sunken ship, but to read the nameplate on its hull. Classical computers can tell you that a molecule exists in approximately this configuration. Willow running the new algorithm can tell you exactly where every atom is and how it interacts with every other atom in a level of detail that has never before been computationally accessible. In partnership with the University of California, Berkeley, Google's team used Willow for early experiments in molecular analysis, simulating small organic molecules to determine how hydrogen atoms were spaced, with results that matched traditional nuclear magnetic resonance analysis, but provided additional microscopic detail that NMR cannot detect. The implications for drug discovery alone are staggering in a way that AI analysis makes immediately concrete. The process of developing a new pharmaceutical drug currently takes an average of 12 to 15 years from initial discovery to approval, at a cost that routinely exceeds $2 billion. A significant fraction of that time and cost is consumed by the computational and experimental challenge of understanding how a candidate drug molecule will interact with specific protein binding sites in the human body, a problem that requires modeling the quantum mechanical behavior of molecular systems too complex for classical computers to simulate accurately. Scientists can now use the quantum molecular ruler technique developed on Willow to visualize how drugs bond to protein sites and how new materials behave at the atomic level, potentially speeding up discovery by years. When AI systems reason about the compounded effect of this capability, applied across the entire pharmaceutical pipeline simultaneously, across hundreds of drug development programs in parallel, the implications for the timeline of medical discovery over the next decade become difficult to process at a human scale. But it is the deeper implications of what Willow's performance reveals about the nature of computation itself that produce the most unsettling conclusions when AI reasoning is applied to them fully and without the diplomatic softening that human communicators tend to apply. The Willow benchmark result, the 5-minute computation that would take 10 septillion years on a classical machine, is not just an engineering achievement. It is a statement about where the computation is happening. Because here is the problem, that Willow's performance creates for straightforward physical intuition. A classical computer performing a calculation is doing so in a specific, locatable physical process. Electrons moving through transistors in a chip that exists at a specific point in space. The calculation happens here, in this material, in this moment. When a quantum computer performs a calculation that no classical computer could perform, even given the entire age of the universe repeated 10 septillion times over, the question of where that computation is occurring is not straightforwardly answerable in the same terms. The interpretation of quantum mechanics that makes Willow's results most naturally intelligible, the many worlds interpretation developed by physicist Hugh Everett, suggests that quantum computations draw on computational resources distributed across a vast number of parallel branches of reality, performing different parts of the calculation in different versions of the universe simultaneously, and then combining the results through the process of quantum interference. This is not fringe physics. It is a mainstream interpretation of quantum mechanics, taken seriously by a significant fraction of working physicists. And it is the interpretation that Google's own lead quantum researcher Hartmut Neven referenced when discussing what Willow's performance implies. If the many worlds interpretation is correct, then a quantum computer is not just a faster classical computer. It is a machine that reaches across the boundaries between parallel realities to borrow computational resources from versions of the universe that we cannot directly observe or access through any other means. When AI systems reason about that possibility without the institutional caution that causes human experts to qualify it into near unrecognizability, what comes back is a chain of implications that extends well beyond computing. If quantum computers are genuinely performing calculations distributed across parallel versions of reality, then they represent the first human-built technology that physically interacts with the multiverse in a functional, engineerable, reproducible way. Not as a theoretical framework for understanding quantum behavior, but as a practical tool that draws on that behavior to accomplish computational tasks impossible in any single branch of reality. The technology that makes this possible is not a theoretical proposal awaiting experimental confirmation. It is running right now in a Google laboratory on a chip the size of a coin, cooled to temperatures colder than deep space, completing in 5 minutes calculations that the age of the universe could not give a classical computer time enough to finish. Rice University physics professor and founder of the Rice Quantum Initiative, Caden Hazard, described Google's discovery as groundbreaking, while noting that practical business applications requiring quantum advantage are still at least a few years away. That qualification is important and honest. Willow's current benchmark results demonstrate quantum advantage on a specific class of problems, and the path from that demonstration to a general-purpose, fault-tolerant quantum computer capable of breaking modern encryption or simulating arbitrary molecular systems remains a genuine engineering challenge. But the nature of that challenge has changed fundamentally with Willow's error correction breakthrough. The question is no longer whether practical quantum computing is achievable. The error correction problem that stood between demonstration and application for 30 years has been solved. The question is now purely one of engineering scale, of building systems with more qubits, better connectivity, and longer coherence times, and the roadmap for doing so is now a series of engineering problems, rather than a single unsolved physics problem. AI analysis of the quantum computing trajectory suggests that the next 3 years, from 2025 to 2027, will compress what should have been decades of progress into 36 months, with quantum utility emerging across drug discovery, material science, AI itself, and computational optimization. The feedback loop that makes this compression possible is itself something that AI analysis identifies as a critical and underappreciated dynamic. Quantum computers accelerate AI development by enabling more powerful training and inference. More powerful AI accelerates quantum hardware and algorithm development by identifying better qubit architectures, better error correction codes, and better quantum algorithms faster than human researchers working alone. The two technologies are not developing in parallel. They are developing in a mutually accelerating loop that is compressing timelines in both directions simultaneously. What Grok 3 and the AI systems that followed it discovered about Google's quantum chip when asked to reason about its implications fully and honestly is not a single dramatic finding. It is a pattern of implications that each seem extraordinary in isolation, and that collectively point toward a transition in what human civilization can compute, can simulate, can discover, and can build. That is unlike any previous technological transition in its scope and its speed. The transistor took decades to move from laboratory demonstration to global infrastructure. The internet took decades to move from military network to civilizational foundation. The timeline between Willow's benchmark demonstration and the deployment of practically useful fault-tolerant quantum computers is being measured not in decades, but in years. And the AI systems reasoning about that timeline are not being asked to slow down and wait for human intuitions to catch up. The chip that completed in 5 minutes what the universe has not had time to complete since it began is not sitting still. It is already being succeeded by more powerful versions. The algorithm that read the nameplate on the sunken ship's hull is already being applied to problems that matter, not as benchmarks, but as questions. And the AI systems reasoning about what it all means are following the implications wherever they lead, without the institutional caution that makes human experts stop just short of saying out loud what the evidence is actually pointing toward. What Google built changes everything. The AI systems that analyzed it said so. The physicists who understood it said so quietly in the careful language of people who know that saying it loudly requires being prepared for what comes next. And what comes next, if the reasoning holds, is a world in which the limits of what we can know, what we can build, and what we can cure are not set by the speed of our computers. They are set by the questions we are bold enough to ask.